we can move on to the sampling methods, where now we are building, having defined the distribution model, which means that we have defined distribution, we can define random variables, we can now proceed to build different sampling methods to be used within UQpy. Now, the current release of UQpy consists of 8 sampling methods. Available methods at this point are the Monte Carlo simulation method, we have the Latin hypercube sampling method, we have stratified sampling, we have MCMC, which stands for Markov chain Monte Carlo method. We also have importance sampling, refined stratified sampling, as well as a simplex sampling method, which basically is a method that allows you to sample within a simplex in a parameter space. Importing a sampling method, importing the sampling methods module is straightforward again, because all you need to do is type in a Python script from UQpy, import sampling methods. But however, as I mentioned before, each module has its own set of classes, and each class can be imported individually. So if someone wants to import, to use, for example, MCMC, and doesn't want to import all other classes of this module, all it has to do is just type from UQpy sample methods, import the method that is required. So basically, the first and the most simple sampling method is the widely used Monte Carlo simulation method. With this class, basically this class utilizes Monte Carlo simulation, which is used in order to generate independent random samples from specified probability distribution objects. I need to mention here that the samples that that the MCS class generates are independent. If one wants to add the correlation between the samples, then the transformation module should be used. Having this in mind, in order to be able to draw samples from this distribution with Monte Carlo simulation, one needs to provide the following attributes. First of all, the distribution name and the distribution parameters, which are attributes required basically by the distribution module. This way, we can define the distribution object that is going to call the RVS function that it's going to be used in order to generate the samples. So as seen in the distribution model, the distribution name is again a string if we have one random variable, or a list of strings if we have more than one random variables. There is no default value for this. This means that it needs to be provided by the user. And also the length and the size of the distribution name defines the dimension of the problem. So if one provides a list that has 5 entries, this means that we have 5 random variables, which means that basically we are in a 5-dimension parameter space. Also, one must provide the distribution parameters. These distribution parameters are going to be used by the SampleMethods method in order to draw the random samples from the corresponding distribution. Again, this can be either an array or a list of arrays, depending if we are on the univariate or multivariate case. There's no default value for the distribution parameters. And finally, what's important, we need to define, the user needs to define the number of samples. There's no default value for that. So if the user wants 1,000 samples from this distribution, the n samples must be set equal to 1,000. And need to mention here that the type of n samples need to be an integer and not a float. Now, we have also some optional parameters, such as the var names, which are used in accordance to run model. Basically, they are placeholders to be used in the case that the Monte Carlo simulation is used combined with a run model module. And also we have the option verbose, which basically it's an option whether or not to print on the terminal. Now, as an output of the Monte Carlo simulation and most of the sampling methods, we have the samples. The samples that are generated according to the specified probability distribution. The samples are an array of dimension where the number of rows is an array of dimension, where the number of rows is the number number of samples that we have specified and samples, and the number of columns basically is the dimension of the problem. So in order to be able to use the Monte Carlo simulation, the MCS class within a Python script, the user needs to type in the Python script from UQpy import sample methods. This way, we import the entire module, samples method module, and from the sample methods module, select Monte Carlo simulation. For example, here, x equals sample methods dot Monte Carlo simulations, and provide all the required input parameters. Now, x here in this case, it's an object. The other way to do this is by importing directly from the sample methods module the method, the Monte Carlo simulation. In this case, x is equal to Monte Carlo simulation, and again by defining all the input parameters. So here we have this is an example of showcasing how we can use Monte Carlo simulation. So in case of where we have one random variable and we provide this name equal to be normal, we provide the parameters of the distribution as a list or an array. We say that we want to generate 1,000 samples from the normal distribution with these parameters, and we define as variable names dummy. This is something that we use in order to showcase that we can also define the names of the random variables. Now, x in this case will be an object, and one of the attributes of this object is going to be samples, which is an array, as I mentioned before. And here is the way to use it when we have two random variables, where again we have to define the distribution names and the distribution parameters. This definition here is exactly the same as we used in the distribution parameters, because these are used by the distribution modules. And again, we define the number of samples and the variables names. Well, in this case, where we have two random variables, we have a list of two names. So again, in the example section, we can find two examples showcasing how to use the Monte Carlo simulation. So if we go here in the example folder and go to Monte Carlo simulation, the first example here is basically an example showcase how to define, how to generate samples according to the distribution from Monte Carlo simulation. So all we need to import is from UQpy.SampleMethod, which is the module import Monte Carlo MCS class. We are going to define, as you see here, we have a two-dimensional problem, which means that we have two random variables. One is normal random variable, and the second one is a normal random variable. So we provided this name as a list of the strings. We have the distributions of each random variable. You see here that we have the standard normal variable, and we want to generate 1,000 samples according to these distributions. So we have run this. You see that we have running, that says UQpy running Monte Carlo, and Monte Carlo sampling has been completed. And now we can plot the samples. We get the attributes of the object. X is an object here, so we have the attribute samples. So if we plot the two columns of the samples, you see that we have the sample at its dimension. And here is the histogram of this sample. So you see it's straightforward to use Monte Carlo simulation or to generate sample. Now the second example that we have is the one that we are using a custom distribution in order to generate the samples. So the custom distribution is defined in this Python script here, where we have defined the PDF, the CDF, the ICDF, and the RVs. Currently, we've selected for this example to use the Weibull function. Now, again, since we haven't defined a fit function, if we call the fit function, we are not going to be able to get the required results. So we have run so one thing to mention here is that for each random variable, one can have a different custom distribution defined at a different Python script. So here you can see the samples. We have the Monte Carlo samples that are generated according to the custom distribution. that we have defined in a custom in a Python script. So this way, one can define the distribution, and an arbitrary distribution can define the function of this arbitrary distribution, write it in a Python script, and then use UQpy in order to define the objects, the distribution objects, and call the corresponding sampling method. Now, similar to the Monte Carlo simulation method, is another option that we have is the Latin hypercube sampling. This method belongs to the family of the stratified sampling techniques, and basically is used to generate samples that in a way that reduces variance between the samples. This sampling approach basically ensures that the samples that are generated are better distributed in the sample space compared to Monte Carlo simulation. Now, basically, Latin hypercube sample has two simple steps. First, you define the range of each random variable to a number of strata that have equal probability, and then at each strata you generate one sample. Again, using Latin hypercube sampling class is straightforward. Basically, as input attributes, you have the same attributes as Monte Carlo simulation, which is the distribution name, the distribution parameters, and the number of samples. But Latin hypercube LHS class has an additional 3 parameters that are called the LHS criterion, which is the design criterion for Latin hypercube. We have 4 options for that. We have the random option, which basically the samples are randomly generated within each strata. In each strata, we have the center, where in each strata the sample is located at the center of the strata. We have the maximum in case where the samples are generated in a way that minimizes the maximum distance between the samples. And we have the correlate structure, we have the correlate option, which basically the samples are generated in a way that minimizes the correlations between them. Now, there's no the default value for the LHS criterion in our case, it's random. Another option that is used in LHS class is the LHS metric. However, this is used only in case that we're using the maximum criterion, and we have 21 possible options for the LHS metric, and the default value, currently the code is the Euclidean one. Also, we have another option called the LHS iter, which defines the number of iterations in case, again, we have the maximum or correlate LHS criterion, and the default value is set 100. 2 optional parameters, like in the MCS class, are the names of the variables defined by the var names attribute, as well the verbal. Now, similar to the Monte Carlo simulation class, the output attributes are the samples, the required samples, which basically is an array that has the samples that follow the prescribed distribution. But also we have an additional attribute that you can see that it's called samples U01, which stands for the samples, the corresponding of the samples in the uniform hypercube. Both of these attributes can be acquired by the LHS class. Again, okay. So again, the way to import and use LHS class is similar to Monte Carlo simulation class. As you will see throughout the presentation, utilizing different sampling methods basically consists of the same steps, and these are import the sample method, either the entire module or the required sample method, provide the required input attributes, run the method, obtain the results, and then post-process the results according to the problem in hand. So again, from the sample methods, we are using the LHS class. We provide all the input attributes. Now, if we need to provide we have some, as I mentioned, we have some parameters that need to be provided, like the distribution name, the distribution parameters, and the number of samples. And the other parameters, in this case, the LHS metric, the LHS criterion, and the LHS iteration are optional, and the user is not required to provide them. So, for example, here, we can only provide distribution name, the distribution parameters, and the number of samples. This is the case where we have one random variable. As you can see, it's again the same way MCS class is used, the same way in the case of two random variables. An example now of LHS class can be found in the folder with the examples. In the example folders, we have the LHS example here, where we have this example. All we need to do is import from the SampleMethods LHS class. And we have different cases where we use, for two random variables, where we have different LHS criterion. We have the random case, we have the centered case, the maximum case, and the correlate case. All of them are defined the same way. The only thing that we need to change is the case here in the string. You see random, centered, maximum, and correlate. And here is the option where we have the LHS design, where we have the random case, where we have the centered for its corresponding case, as you can see. So basically, using a Monte Carlo simulation class and LHS class is basically, you do it the same way. What the user needs to provide is the distribution name of the random variables. You need to provide the distribution parameters, and you also need to provide the number of samples you want. In the case, moreover, in the case of Latin hypercube sample, there are some additional parameters that one needs to provide if required. But however, using those two sampling methods is pretty straightforward, and the output is a vector, is an array of the required samples. Now, as we move forward to the sampling methods, I will pass on to Audrey Olivier, that she's going to talk to us about Markov chain Monte Carlo simulation method and sampling.
Looks good.
Okay, thank you. Sorry about that. So I'm going to be talking about MCMC Markov chain Monte Carlo. So the idea here is that you want to sample from a distribution P, knowing that you can't necessarily compute P of X directly, but you can compute a scale version of it. So that would be my P tilde here. Okay, I can't show you anything, but that's whatever. So you can compute a scale version of P tilde. Your mouse is really weird. And so that actually is going to arise a lot when you do Bayesian inference. And we're going to be talking about that tomorrow, but so MCMC is used quite a lot for Bayesian inference. So the solution here is that you're going to sample from a Markov chain whose stationary distribution is the target distribution P. And one well-known algorithm is the Metropolis Hastings algorithms, and it basically goes as follows. You initialize your chain using your seed sample, and then you walk your chain, where one move of the chain goes as follows. First, you sample a candidate X star using your previous sampled and a transition PDF cube. And then you either accept or reject that candidate based on a certain probability of acceptance alpha, which you can see the equation here. And so either you accept a candidate X star or you propagate the previous sample X. And the idea is that at the end of that, you iterate this step and you end up with a set of samples that are distributed according to the target distribution P. So in UQpy, the only thing that the user must define is the scale target P tilde and the transition PDF cube. Okay, that worked. So first, with P tilde, it's going to be defined through the inputs PDF target or log PDF target, one of the two. Basically, the code is going to check the existence of these inputs according to the graph that's shown here. First, it's going to check is log PDF target is defined. And if yes, it's going to check how it is defined. So if it's a callable, then it's just going to be used to compute log P. If it's a string, then it's going to build a distribution from the distribution module that we saw before with Dimitris, where the input this name is going to be this string log PDF target that you're giving. And then it's going to use this the log PDF method of this distribution to compute the log P. So this distribution must have a log PDF. If log PDF target doesn't exist, then it's going to go and check PDF target, and it's going to be the same story again. So it's going to check whether it's a callable. If it's a string, it's going to build a distribution, and then it's going to check if that distribution has a PDF method. Okay. So all the callables that we are defining here must be a function of at least one variable x, and they can also be a function of additional parameters, params, and copula params. In that case, you would need to give those parameters as input to MCMC as PDF target params and PDF target copula params. So this is how you define your p-type distribution. Okay, and the other thing that's important in how you define MCMC is the transition PDF queue. And this is going to be, it's going to be defined using PDF proposal type and PDF proposal scale. So the type is either uniform or Gaussian. And then the scale, it governs the size of the jump. So I've plotted a few examples here where you can see what happens depending on the scale parameter. So, so the three plots here, you're sampling from a two-dimensional Gaussian PDF. And basically in blue, I showed the samples that are accepted. And in red, I show the candidate samples that are rejected. And you can see that if you have a very small scale parameters, you just, you walk your chain very slowly, and so you do not explore the space enough. But then on the very right, the third plot is that if you have a scale parameter that is too large, you're gonna go and sample too far away from your distribution. And so you're gonna reject a lot of samples, and that's gonna be extremely inefficient. So this scale parameter is extremely important in how MCMC is gonna work out. Another set of inputs that also govern the number of samples that you're gonna generate. So first is n samples, it's the total number of samples that you're gonna be, that you're gonna get at the end of that process. And then you also have n burn. So the idea is that when you start working your chain at the very beginning, you're usually not, you're not sampling from your target PDF yet. You have to wait a little bit to get to convergence, and that beginning part is called the burn-in period. And so you would want to reject those samples that are not sampled according to the target PDF. So n-burn allows you to reject some samples. And then the other thing with MCMC is that it's going to create samples, it's going to generate samples that are correlated to each other. So if you want to have samples that are approximately IID, you need to keep only one out of so many samples, and that is governed by the jump parameter. So at the end of the day, the total number of simulations that you do is n-burn plus n samples times jump. By simulations, I mean the number of times you evaluate p tilde of x. So if that's computationally expensive, then you can have to be careful about that. So now I've been talking about Metropolis hastings, but UQpy also supports two other enhanced algorithms. I'm referring you to the user manual for more detailed explanations, but basically the modified Metropolis hastings algorithm, the jumps are performed separately in each dimension. And you can use this algorithm by setting the input algorithms to the string MMH. And then the other algorithm is it's called the affine invariant ensemble sampler stretch moves, where here you build an ensemble Markov chain with several walkers. And so you can use this algorithm by setting the input algorithm to stretch. And the difference here is that the algorithm required several samples as seed to the different workers. So when you initialize your algorithm and you give it seed, it has to be an ND array, so of size L times the dimension of your problem. So here we summarize the input attributes of the class MCMC. So the first thing that's important here is the first one, it's dimension. Basically, the dimension is the dimensionality of your random variable X. And so it's very important that you set that right. I've talked about the two other required input attributes, which are either log PDF or log PDF target, as well as n samples. Yeah, I think I've talked about all the parameters, the input parameters that you need. And then the output parameters are, so the samples, it's an ND array of size n samples times dimension. And then the accept ratio is the acceptance ratio of the chain. And so it gives you an idea of, it's one of the things that gives you an idea of how good your MCMC algorithm is. You would want probably something between 10–50%, but that's kind of depends on your problem. But and here we get into how you actually import the MCMC class. So it's the same as all other classes. You just do an import SampleMethods or an import MCMC, and you give it all the input attributes that it needs. The other thing I wanted to mention is that we have a diagnostics module that you can run for MCMC. So as I've shown, depending on, for example, your scale parameter, you're gonna end up having a good set of samples at the end of your MCMC or not. And so the accuracy of your estimation depends on a certain number of parameters. And the diagnostics, they compute, for example, the effective sample size. They also show you some plots of your Markov chains, convergence, and that gives you an idea, qualitative idea of how well you've done using MCMC. And so you can use those diagnostics to set the scale parameter, the burn-in, the jump, all those parameters that are going to be important for the accuracy of your estimation. And then I'm going to go to some examples. So here, just to do that. Okay, that worked. If you want to see where they are, so again, in the example folder, you go to MCMC, and here we have two folders. So I'm going to show you example 1 here. So the basics, you do the right imports. So the things that's important here is how you define your target PDF. So here in box 2, I'm showing you 3 different ways that you can define your target PDF. So here our target PDF is the Rosenbrock. So you can define it in a way, so here it's defined as a callable. You can see it's a function. It can be defined taking as an input only the random variable X. You can also define a function that takes in another input params. You can also define the log PDF instead of the PDF. And when you call MCMC, so the Rosenbrock is in dimension 2, so you need to give it dimension 2. You need to give it a proposal type and a proposal scale. The proposal scale has to be in the same dimension as dimension. And then, so you can set PDF target to, so for example, in the first one, I'm using the first that do not take in any parameters, which means that then you set PDF target params, this input here, as none, because you do not use any parameter in your callable. Define the algorithm, jump, and samples, everything I've been talking about. Another way of defining it is that now you use as a callable this function Rosenbrock that uses a parameter as an input. And then in that case, you need to give it the parameter within PDF target params. The rest is the same. And finally, you can define a log PDF instead of a PDF. So then the input that you would use is a log PDF target. Same here, it doesn't use any parameters, so you use PDF target params equals no, or you do not set it at all. So those examples we're using the Metropolis Hastings algorithm, but you can use MMH. So I refer you to use your manual, but MMH also use another input, which is the PDF target type, and that defines how your acceptance ratio is going to be computed. You can use the stretch algorithm. So here in the stretch algorithm, you can see that the seed has to be given, and it's an ND array of several samples. And so basically here what we did is that we used the previous samples that were generated using MMH as a seed to start the stretch algorithm. So this is one good way to use that algorithm. So here, so you can do some comparison of computational time, and here I'm just trying basically the three PDFs that you get using the three algorithms. Obviously, you would expect them to be the same. And so the other thing I wanted to show you is just the second example, which is it's exactly the same as the first one, except that we do not define the PDF in the same way. So again, the same imports. So and the important part is box 2 here. So we call MCMC, but now the PDF target is the string called Rosenbrock. And so basically what this thing is going to do is that it's going to build a distribution using this name equals Rosenbrock. So it needs to have a .pi file, Rosenbrock, that defines a distribution. And I'm showing it to you here. It's this file, and you can see that it has a PDF method, which computes the PDF. Okay, and you can see that it takes as an input parameters, both X and params. So you need to give it some parameters here within PDF target params when you call MCMC. Now, one thing that would not work is if you define Rosenbrock as the input log PDF target. The reason why this wouldn't work is because this file here that defines the distribution does not have a log PDF target. And so the MCMC algorithm is going to check whether that distribution can compute a log PDF, and it's not going to work in this case. So you're going to throw an error here. And then the rest is exactly the same as before. We have a little additional example in dimension 2 here again, where you can give it as again a PDF target to a set of 2 strings, the same for the PDF target params. And so this is going to use the distribution that are already within UQpy that Dimitrios just talked about before. So that is it for MCMC. Okay, now I'm going to talk about important sampling. It's another way to sample from a distribution, and that can be used where when you can't generate sample easily from the target PDF, but you can generate them from an importance distribution, so a slightly different distribution that I named Q here. Another place where it might be interesting is if you want to compute expectation over the random variable X, but you know that your function is very small outside of a small region. So what you would want to do is really focus your sampling around that region. So then you want to sample, basically you want to sample from a different distribution than your actual target PDF. So the idea behind important sampling is that you sample from an important distribution, Q, and then you weight those samples according to the likelihood ratio. So basically the weights, they account for the fact that you haven't sampled from the true target, but you sampled from something that's different. So you need to account for that. Again, if you cannot compute P directly, but you can compute a scaled version of that, then you can do that with importance sampling. It's called self-normalized importance sampling, and this is actually what UQpy does. So if you have a scaled version of P, that's fine too. And what you get at the end is a set of samples and their weights. So for example, here on the right, you can see a plot where we sampled from a uniform distribution over the square that's shown here. And then the cut target PDF is the 2D Gaussian that's shown in gray. And so what you get out of that are a set of samples that are in red, and then they're weighted. And you can see that the weight is proportional to the scale of the point is proportional to the weight. So this is what you get out of importance sampling. Again, in UQpy, the user must define the target PDF as well as the importance distribution Q. So the target PDF is the same as before for MCMC. You define either PDF target or log PDF target to evaluate log of p-tide. The only difference here is that you need to be careful that log p of x is going to be evaluated on all the samples that you've sampled at once. So the callable that you define has to be able to compute log PDF for an array of size n samples times dimension if you define a callable. I'm going to show that in an example. The definition of the proposal PDF, it's through the input called PDF proposal, and it must be given as a string or a list of strings, and then we're going to call a distribution, the distribution module, using this name equals PDF proposal. If this distribution requires additional parameters, they should be given to importance sampling through the input PDF proposal params. The very important thing about this proposal distribution Q is that it must have an RVs method, because we need to be able to generate samples out of it. And it must have also either a log PDF or a PDF method in order to evaluate log Q of x. And again, log Q of x is going to be evaluated on all the samples at once. So here is a summary of the input attributes of the importance sampling. So there's a small mistake here. There are actually 3 required arguments. So the PDF target or log PDF target, the number of samples that we've generated out of that process, but also PDF proposal is also required. There should be an X in that box here. And again, it has to have an RVs method and a log PDF. Then the other 4 are just parameters that are needed or not, depending on how you define your proposal and your target. And the output that you get out of that process are the samples that you've sampled from Q and the weights, the importance weights. And you import importance sampling in the exact same way as you would import any other class here. And again, we have a diagnostics for importance sampling. So the idea here is that you may actually end up with a lot of samples which have very negligible weight. So weight that's almost 0, and only a few samples are going to have significant weight. And so you actually only have a very few interesting samples. And so the diagnostics help you kind of figure out if you have enough samples to actually obtain an accurate estimation of your posterior PDF. So I actually have an example for that somewhere. It's a really small example. So again, you go to example, it's in importance sampling. So it's a very, very small example. Basically, the only thing I want to show, so if you run it, is that, so it's the same Rosenbrock function, but here you can see the difference is that when you evaluate log Rosenbrock, it has to be able to evaluate it over an NT array of size and samples dimension. So you have to be careful when you define the log Rosenbrock function here. That's the only thing that's changing. So here I'm sampling from a 2-dimensional uniform PDF. So you have to define PDF proposal params, and the log PDF target here, because I'm defining a log PDF in log Rosenbrock. So yeah, that's and at the end you get a set of samples, and here you can just see that I'm using a function called resample. It's also in the utilities of UQpy, and basically it's if you need, so as an output of importance sampling, you have a set of samples and their weights. If you need only samples that are all uniformly weighted, then you can use this resample method. I'm going to let you get into the user manual for that. But then you end up with a set of samples that all have the same weight. And this is all I had to say about MCMC and import assembling. So I'm going to leave the floor.
Hi everyone, my name is Mohit and I'm going to take us through STS, RSS and simplex class. So STS class generates random samples using stratified sampling method. It is a variance reduction and space filling technique. To understand how it works, there is a simple example in one dimension. So basically we divide the 0 to 1 domain into n different stratas. In this example, it's like I've divided it into 4 groups, and we generate one sample from each strata, and using inverse transformation, basically we get the samples. So the thing here is that STS class generate only one sample per strata, and the way it works, we only need to define the cumulative distribution function of random variables and the stratification of a hypercube. So here are the input attributes of STS class. So we have this name, which is basically a string. If we are working in one dimension, if we have a one dimension case, it is only one string which defines the distribution of a random variable, and these parameters are basically its parameter. And if we have more than one random variable, then these this name can be a list of strings, and parameters can be a list of n-dimensional array. So these two attributes are basically required to define the cumulative distribution function. And the other thing which we need is we need to define the stratification, and for that we have STS design and the last attribute, which is input file. So these two attributes basically used to define the stratification, and I will come back to them and explain them in details in a second. And other attributes are dimension. So dimension is basically the dimension of our input space, and it is not required when we are using STS design, because our class basically directly take the dimension from the STS design. And if we are using input file, then dimension is required. And STS criteria is basically a string which can be random or centered. So once we have defined the stratification, random basically generate a sample inside each strata using randomly generate a new sample inside each strata using uniform distribution, and centered criteria basically gives us the center of each strata. And as an output of STS class, we have the samples which we want. It is going to be an n-dimensional array, and sample U01, which is basically the samples in 0 to 1 domain, which we get before the inverse transformation. And strata is a class object which basically contains the weights origin of each strata, origin, weights, and width of each strata. I will come back to this again in a second. So yeah, as I said, to define the stratification in STS class, we have a strata class which basically takes n strata and input file as attributes. So, and as output attributes, we have origin, width, and weight. So let me first explain how we can use n strata to basically generate a stratification. So if let's say in a two-dimensional case, if we are sending a list 2,3, basically it's divide the first dimension into equal groups, and the second dimension in 3 equal groups, and basically divide stratification, which you can see on the bottom of the right side, and the output attributes, which are basically origin, width, and weight, are like this. corresponding to each strata, we have its origin, which is the left bottom coordinate, and widths are basically length of that strata along each dimension, and dates is basically the product of the width in this case. And so the way this works is that it along each dimension, the width is same for each strata, and the weights are equal for every strata. And so we can also define a custom design for which input file we can use input underscore file. We can define a text file in this way, like this is an example for two-dimensional case. So if you see this file, then first two columns are basically the coordinates of each strata, and second two columns basically shows the width of each strata along each dimension. So this is just a case in two-dimensional case. If we have like more than two-dimensional, like in three-dimensional case, then we will have basically 6 columns. First 3 columns will show the origin of each strata, and the last 3 columns will give the width along each dimension. So yeah, these two designs can be used to define the stratified stratification, which is basically used in stratified sampling. So yeah, so here are the way we can use following command to import the stratified STS class from sample method module. And here are the 2 examples. Like in first case, when we have imported sample methods.sts will basically call our STS class. And here in this example, we are basically using a two-dimensional case where we have 2 normal distributions, one with mean 0 and variance 1, another with mean 2 and 1, and variance mean 2 and variance 1. And basically, as STS design, we are basically sending a list which break each dimension in 5 groups and kind of create 25 stratas. And in the second case, you can see it's a 3-dimensional case, and you can define an input file and use it. So let me take us through the examples for this. So here is the first example for the stratified sampling class, and in this example, we have used a basic design, which is basically STS design and how it works. So yeah, we imported the STS class from the sample method module, and you can see here this STS design is 5,5. So basically, weights are going to be equal and widths are going to be equal along each dimension. And yeah, so this figure is basically what we are getting from strata class. Each dimension is divided into 5 groups, and we have kind of 25 stratas. And after doing the inverse transformation, we have these following samples using stratified sampling. And you can, as I said, strata class is an object, is also an output of STS class, output attribute of STS class, and which has weights and weights, origin, and width of corresponding to these samples. And these are the 25 samples which are generated in this example. So in this second example, we have used the input file to define our stratification. So we should file. So this is the input file where first two rows gives us the origin of each strata, and second two rows give us the width of each strata. And if we go through the example script, we can see this is the stratification which we have defined using the text file, and we have one sample is generated inside each strata, and then using inference transformation, this is the final samples which we get. Okay, so that's all about STS class. Now let's move on to RSS class. So RSS class also generates random samples, and it is an adaptive method which uses initial input design. Basically, there are two approaches in RSS class. Basically, first approach is refined stratified sampling, and second approach is gradient enhanced refined stratified sampling, which is also GE-RSS. So GE-RSS basically uses gradient to reduce the variance of the output estimate, and refined stratified sampling does not do that. So the main difference between how we can use them is that if we give a model, then RSS class simply use gradient enhanced refined stratified sampling. If we will not define a model, then it simply use RSS. And since I said GRSS uses gradient to reduce the variance, we have two approach to compute the gradient, which is one is basically linear interpolation, and second is Kriging meta model. So here is how refined stratified sampling works. Given a stratification, first step is to look for the strata which has the maximum weight associated with. If we have multiple strata which have same maximum weight, then we randomly choose one among them. Once we have selected a strata, we are going to divide that strata in half along the maximum dimension. And if we have more than one direction which have maximum width, then we will randomly select a direction among them and break our strata in half along that direction. And once we have done that, third step is to randomly generate a new sample inside that strata, and keep on repeating that step until we have reached the desired number of samples. And in case of gradient enhanced refined stratified sampling, we estimate the variance associated with each strata. We look for the strata with the maximum variance, and we select that strata to break into half. In the second step, we look for the dimension which has the maximum gradient associated with, and divide that strata along that direction. And once we have the new strata, we just randomly generate a new sample inside it, and keep on repeating until we have desired number of samples. So here are the input attributes for the RSS class. So X is basically a class object which should be coming from STS class or RSS class. Basically, it has the initial input design on which RSS class are going to build and generate new samples. And samples should be integer, and basically the number of samples, final number of samples which we need. Meta is the method we are going to use to generate which we are going to use to generate a surrogate and find the gradient. And cell is basically a string which could be rectangular or walnut. if we do rectangular stratification, the string should be rectangular, and Voronoi cell are there. We are still working on it, and it will be there in next version. Model basically is required if we are doing GE-RSS, and it calls run model class to evaluate the model at the samples we have generated. And so as we see, it uses run model class. Right now it only works with if we have sending a Python model, but if we try to use the third-party software, then RSS class will not work as if right now. And so minimum train size is the number, should be an integer, and basically while finding the gradient, when we are defining a surrogate, it's the minimum number of samples to update the surrogate locally. Step size is basically used when we are using linear interpolation to estimate the gradient, because after doing linear interpolation, we are using central difference to calculate gradient, and basically the step size is the step size in the central difference. And these attributes, next 4 attributes, correlation model, parameter, regression model, and optimization, are basically used to define kriging, which I will explain them later tomorrow in the surrogate section. So yeah, and as output attributes, we have samples and values. So samples are the final samples which we wanted using the adaptive approach, and values this will be only there if we are using GE-RSS. This will not be there for if we have not sent the model, then definitely values will not be there. And yeah, so yeah, here is we can import RSS class using following command. If we have used imported sample method, then sample method dot RSS can be used to in this way. And basically you can see X equals to object should be an STS or RSS class object. Model is only required if we are using GE-RSS, otherwise model is not required. Meta is same. If we are using GE-RSS, it is required, otherwise it is not required. Cell is equals to rectangular, and minimum train size is also required when we are doing GE-RSS, otherwise it is not required. And n samples is final number of samples which we want, and other quantities are related to kriging. So let's go through the examples we have for RSS class. So here is an example for refined stratified sampling. So as I said, it is an adaptive approach, and we need an initial design, which is in this case is generated using stratified sampling class. So basically, it's in a 2-dimension case. We have 2 uniform random variable between 0 and 1, and this is the stratification which I have used. And as you can see, the way RSS class is used is X is basically should be a class object from RSS and STS class. And since here I have used STS class, and I have initially I have used started with 16 samples, and final sample is 18, and I have used rectangular stratification. So here you can see this is the initial samples which we have generated using stratified sampling, initial 16 samples, and these 2 inside the blue box are basically the new samples which we have added using refined stratified sampling. And further, you can see here that here I have again used RSS class, and this time in X is basically a class object which is coming from RSS class only. You can see Y was coming from RSS. So now I have which already have 18 samples, and which we have adaptively increased till 100 samples, and rectangular stratification. And this is the final 100 samples. Okay. So here is an example on GE-RSS. So again, here I have used stratified sampling to generate our initial design, and you can see here this is the initial 16 samples. So here I have defined a model, and I'm using a model to evaluate the model value as all these initial samples. And basically this is the model singularity function which I have used here in this example. And you can see here, in order to use GRSS, using RSS class, I have sent in the initial design, basically STS object, and I have defined a model here, which is basically this function. And in this particular example, I am using linear interpolation to estimate the gradients, and the final number of samples is basically 200, and minimum train size is defined as 100. And you can see this is the final number of samples. The red dot basically shows the initial samples which we had, and blue crosses are the new samples which we have generated. And the box shows the stratification, and you can see we have only one sample inside each stratification. And so here is another example on GE-RSS. Again, the difference between previous and this example is that gradient is estimated using kriging instead of linear interpolation. So here I started with generating initial design, which is generated using STS class, that is 16 samples. And for the same function, you can see this is the using 16 samples. If we generate a kriging surrogate, it looks like this. And so here I have generated kriging surrogate. I will explain this tomorrow in more detail. And so the way RSS class is used, you can see here meta is defined as kriging, and same 200 sample is generated starting from 16 samples. These quantity regression model, correlation model, these are related to kriging. And these are the final samples. These red dot basically define the initial 16 samples which we had, and the cross define the final samples which we generated. And this is basically the final surrogate model using the 200 samples. Yeah. Okay, so I will give it back to Bhavesh now.
Okay, thank you. So that's going to conclude our training for today. And so, just as a quick recap, we covered the introduction to how you run a model with UQpy, as well as how you define a distribution in UQpy and various sampling methods that are used. These things serve as the core of the UQpy software. Tomorrow, when we reconvene at 9 a.m. Eastern Time, we will talk about some of the capabilities that UQpy has, specifically around surrogate modeling and Bayesian inference and inverse problems and other inference problems, as well as reliability problems and stochastic process and random field generation. So thank you again for attending today, and we look forward to seeing you all again tomorrow.